Welcome everyone to the April 2021 Soils Network of Knowledge webinar. I'm Abigail Jenkins, one of two Soil Development Officers with New South Wales DPI. The other is Luke Benj in Dubbo, and we convene these webinars. So I'm going to introduce John Medway now. So John's a Senior Research Fellow specialising in spatial agriculture at Charles Sturt University's Graham Centre. But his history in farming goes right back to growing up on a family farm on the Liverpool Plains in New South Wales and completing an agriculture science degree at Charles Sturt Uni in the mid-80s. He spent some time in the corporate farming sector before returning to CSU as a research officer at the Farrer Centre, working with a local farmer group, comparing farming systems and demonstrating the role of objective monitoring for improved crop management. This work included the investigation of spatial variability through the use of remote sensing, soil surveying, and yield mapping. Then in 2000, he established a spatial data consultancy, and over its 21 years of operation, John's worked at over 2,500 projects across Australia and internationally, providing services to family and corporate farms, industry, research organisations, and government agencies. Right now, he's working with the Graham Centre on the Charles Sturt Digital Twin Farm and the Cool Soil Initiative projects. So he's very well placed to present the webinar today, as you can see.
Okay, thanks, Abby. Welcome everyone this morning for the today's presentation, and thanks for the opportunity to have a bit of a chat about some of the spatial processes and data that I've been looking at now for over 25 years, mostly here based here in the Wagga area, but data from all over the world, essentially. When we think about patterns in paddocks, anyone who's walked through a crop, driven past a crop, flown over a paddock, paid any attention, will notice that there are patterns. There are patches, there are obviously good bits, obviously bad bits, and quite often have wondered, well, why are they there? And sometimes those patterns are just naturally occurring. It's the underlying variability of something in the landscape, but there are also plenty of other instances where the patterns are very much man-made or induced or management effects. And so how we identify those different types of patterns and causes and investigate them is really quite different. As well as those sorts of visual sort of crop effects, there's also, for anyone who's been in a paddock with a shovel or a soil sampler and taken soil cores, knows that finding a uniform soil is relatively difficult to do. That soils are inherently variable in the Australian landscape, and that for decades and decades, researchers, farmers, agronomists were trained essentially on how to try and sample paddocks on an average basis to try and counter for the variability that's just naturally occurring in the landscape. In 1995, that largely started to change with the advent of GPS, which fairly quickly presented a whole heap of technologies that could allow us to actually specifically locate our observations and take account of that variability, rather than trying to come up with a best fit average. And possibly the thing that stirred most interest from a farmer perspective was the availability in 1996 of yield mapping. And what we have here on the screen is the very first yield map, the very first paddock that I yield mapped in 1996 in a farm about 10 kilometres west of the university here in Wagga. 96 was a pretty good year. And this particular paddock averaged 6 tonne to the hectare, but within that paddock, there were patches that were going 9 tonne and other patches that were going 3 tonne to the hectare. So it was really quite an eye-opening picture, I think, for most farmers, advisors, researchers, just the extent of or the range of that variability. And it just raised all kinds of questions. Well, what are we going to do about it? How are we going to manage that variability? Because it seemed pretty obvious to a lot of people at the time that all we needed to do was to get out and soil sample those low yielding patches, identify what the nutrient limiting the yield was, variably apply it, everything would be happy. 25 plus years later, that's not quite the way it's panned out. So going back to those 1997 options and identifying some of the variability, that there are obviously some logistical aspects that we could manage much more efficiently using GPS. So vehicle guidance and machinery automation technologies were pretty much instantly on the scene, and they've continued to develop quite amazingly over that time. And so it's not uncommon to see in research locations, facilities now that there's plenty of autonomous machinery now racing around the countryside, mostly at small scale, but it's getting larger and larger, and it's not too much of a stretch to think that in the next few years, large autonomous vehicles racing around paddocks doing whatever it is they need to do is going to be commonplace. And if we're going to get the best value out of those technologies, then we actually need to understand a lot more about this variability so that we can come up with reliable management strategies. Back in 1997, at the first of the Precision Ag symposiums that Sydney Uni hosted, there were almost two camps of thought as to how we're going to manage variability. The first was, as I mentioned a moment ago, all we needed to do was simply grid soil test, come up with a grid variable rate application plan for fertilisers, and magically yields will be uniform. It didn't take too long at all to show that that wasn't going to be the case, that nutrition isn't often the primary limiting factor in causing variability, and it largely ignores the fact that there's actually different yield potential in different parts of the paddock, and so it's managing potential is probably where is a better approach. Alternate to the grid sampling approach was simply that in the first instance, what we should be doing is some targeted investigation, simply recording where we're doing our observations, trying to identify where is the most representative part of a paddock, so that we can then perhaps come up with better whole paddock recommendations. Because at the time, to fit a variable rate controller to an air seeder with a GPS and some software, you're looking at about up to a $50,000 sort of aftermarket modification to the equipment. So it was actually a pretty expensive exercise to conduct. And so there was some reluctance to go down that way, or that path, until we really knew what was going on. There are also plenty of people who just didn't know what we were going to do with the variability. And there are others that said, well, let's just wait and see what happens. But we pretty much sort of jumped into investigating variability and looking at soil patterns and soil yield. And the first thing that became immediately obvious was that if all you have is a single piece of information, that can actually be more dangerous than having no information at all. And so what we have here is a soil map based on a conductivity survey that, when we went out and did some targeted soil sampling, identified that these green and blue areas, which were the low conductivity zones, had a pretty common low soil nitrogen availability, 0 to 60 of 70 kilograms available N, whereas the high conductivity zones of the paddock were 180 kilograms of available nitrogen. And for over 20 years, I've been showing this map to our students and farmers and asking which part of the paddock, if you're about to be putting a wheat crop into this paddock, would you be putting most of your nitrogen fertiliser? And after 20-something years, without exception, I'm still waiting for someone to say that more fertiliser needs to go on the end of the paddock where there's already 180 kilos of available nitrogen. If that's the only number we've got, that might seem to be a reasonable assumption to make. But if we make the observation of what the soil type was like at the time of the sampling, and continues to be, is that these low conductivity zones, the soil was actually only 30 or 40 centimetres deep. It was a heavy black clay soil. In the red zone, the high conductivity zone, the soil was metres deep. And so it might well be that these two areas of the paddock have actually got very different yield potentials. And so it could well be that 70 kilograms is more than enough nitrogen to satisfy the crop in this low conductivity shallow soil, and that actually 180 is not enough nitrogen to reach potential in a really deep black cracking clay soil in northern New South Wales. So it highlights the fact that we really actually need to understand the landscape, not simply go out and have isolated pieces of information to you know, take us down this track. And so we go back to how do we understand the landscape, and yield mapping really is an excellent way of doing that, because it's telling us sort of without sort of favour exactly how a paddock is performing. So it can tell us in an individual year where are the low producing areas and where are the high producing areas. But most farmers will tell you that the patterns aren't always consistent. They can flop from one year to the next. And so it can actually be useful to take multiple years of information, and if we can stack that up over years and years, we can generate a map that says, in this instance, over 7 years, this red zone in the paddock in the northwest corner has removed up to 24 tonnes of grain, and these blue areas over 7 years have produced as little as 7 tonnes of grain per hectare. And when we start showing maps like this to producers, it becomes much more obvious that they'd really like to be doing something about it, but they'd like to understand more about the patterns and what's involved. And also, because of seasonal conditions and things, it can be quite a different scenario from one year to the next, one paddock to the next. And so it might be that actually generating an average yield is a better way to go. So using that same data now, it's a relatively straightforward process to take multiple years of data, normalize that data. So within each year, the average yield has a value of 100. So you can then generate an average picture, which then tells us that on average, this red zone is producing up to 40% above average. These blue areas on average are up to 60% below average. And they're the kinds of numbers that yield mapping really just highlights, that there's plenty of patterns out there in paddocks that warrant further investigation. But if we are going to go down that track, then the quality of the data becomes quite critical, and that data really does need to be processed, needs to be firstly collected appropriately, processed appropriately, so we can get to good, clean data on which we're going to be basing decisions. And so the map here on the left shows all the raw data individual points, and so all these red points are the low yielding, the green is the high yielding, and there's a whole range of artifacts that we can see in there. And so this area of red across the middle of the paddock, it's not that there's actually a low yielding part in that paddock, but what's happened is that this particular farmer likes to harvest a strip through the middle of the paddock and place his field bins in the middle of the paddock. So then proceeds to harvest. So then as he continues to harvest, every time he passes over that area, it records a low yield. So there's a whole range, and the same as going around trees, finishing off strips. There's just lots and lots of unreliable data in a lot of yield maps, particularly in mixed farming systems where there are lots of scattered trees or other non-crop areas within paddocks. And so now it's a relatively straightforward process to run an algorithm that can identify all those points and generate a nice clean set of data, which we then use to be processing the data to generate our zone maps or to target and inform our investigative activities. Not all farmers, however, do have access to yield mapping, and so there's now a range of remote sensing options. And well, remote sensing actually predated the yield mapping, and so it doesn't really matter whether we're using an aircraft, a drone, or a satellite. There's a dozen different ways of being able to take a nice infrared picture or a multispectral image of a crop at all kinds of different scale, from millimeters up to tens of meters. Depending on what the issue is that you're interested in looking at, you then pick a resolution that's going to be able to identify and solve or assist with your field activities. And so using these technologies, we can quite easily generate a crop vigor map that shows us where are, at this particular point in time, the high growth areas and the low growth areas. And whereas back in the 90s, it might have taken 3 to 4 weeks to get access to a satellite image after the satellite had passed over, it's now possible to be getting the satellite data within about 2 hours of some of the satellite systems as they pass over. So there's no time lag there at all, really, in being able to access the data. But then also we have a multitude of drone options if the scale of the issue and the scale of your area is appropriate for using drones. And so it really is, I think, much more important to look at what's the scale of the project and tailor your data capture system to your problem, rather than being fixated on any one particular technology. And so real-time imagery is a fantastic option. But we also now have access to loads and loads of historical imagery. So the US government has been conveniently taking a picture of the planet every 15 or 16 days, going right back to the 70s. And most of that data is now freely available. And for anyone who's got the software who can process it, you can download, in this case, the last 9 years worth of imagery for a farm, generate a vigor index for each of those years, stack them up, and then generate a nice overall average picture, which shows that on average, the crop vigor, and this is just a biomass measurement, not a crop yield assessment, but it tells us that these green areas on average have a higher biomass than these brown areas. So the technology is not diagnostic. It's not telling us why the issue is there. It's just telling us that there is an issue, or that there is a difference. It doesn't even tell us the magnitude of the difference. It's just telling us here are patches that are different. Someone needs to go out into the paddock and start investigating why they're there. And a really good way of doing that, and particularly at large scale, is using some of the automated mapping technologies that have been available, for decades as well. So whether it's electromagnetic or radiometric surveying, we can hook up sensors to a vehicle, whether it's a tractor, a ute, a quad bike, drive across a paddock at fairly close intervals, and generate a map that shows how the conductivity of the soil varies. And the conductivity, while it's directly a measurement of the salt content of the soil, the soils don't have to be salty. It just, every soil has a background level of salt in it, and so we can generate a pattern. But what we also find is that typically the distribution of salt across a landscape is based on the drainage characteristics of the soil at that local area. So an area, a soil which has high drainage characteristics will have had more of the salt washed further down through the profile than an adjacent area with lesser drainage characteristics. So in these maps here, again, they're not necessarily diagnostic. What they're telling us is that these blue areas are likely to be lighter textured soils with higher drainage than the red and orange area soils, which are the high conductivity zones. If necessary, we can run that conductivity data through advanced software, which then starts to identify specific locations to go out and take soil samples from, which can then be used to generate specific maps related to exchangeable sodium, pH, deep drainage characteristics. That can then be taken through to be generating variable rate application maps and things. So there's a range of things that we can be doing once we start identifying the trends in the soil characteristics. Perhaps the most substantial changes in conductivity surveying, particularly in the last few years, is the ability to do multi-layer investigations. And so that's where we can have sensors which are able to analyze multiple depths simultaneously, which allow us to generate a profile view of the landscape or of the soil, or to even take that to a three-dimensional picture of how conductivity varies both down the profile and across the landscape, which again can be an incredibly useful tool for directing us where in the paddock we go to be to investigating what's going on. Ideally, rather than relying on a single source of information, as we were talking about earlier, it's an even better scenario if we can take multiple types of information. So if we can take landscape information, soil mapping, imagery, yield, it can be multi-years of imagery and multi-years of yield data, run that through a statistical process to generate a productivity zone map, which then tells us, in this case, that the red part of the paddock is producing differently to the green part of the paddock. It's a reliable statistical analysis. It's more robust than laying a series of maps out on a page and asking an individual to say, well, where do you think the zones are? It's a mathematical process. It doesn't matter who presses the buttons. Depending on the parameters you've used, is how the map will generate. And once we've got a zone map, we can then, I think in the first instance, the best thing to be doing is to actually be stepping back from the landscape, not wanting to drill right into individual paddocks and individual sites, but to actually step back a bit and say, well, how do those different patches and zones within a paddock relate to the landscape, and what might be the general characteristics that are there? And so in this case, a farm with the productivity zones within each paddock identified. We then go out and take 15 or 20 or however many metre and a half soil profiles and actually describe the soil landscape. And once we've done that, we can then identify where are the areas where drainage is likely to be an issue, where it might be pH, where it's compaction, where it might just be new. It can then give a much informed analysis of where we need to be going out and doing more detailed investigations. And when we do those detailed investigations, it might be that we are just going out on a zone basis. And so in this case, we're going out and taking our 30 or 40 subsamples within each zone to come up with an assessment for the zone characteristics. Or it might be that we've been able to go out and for a particular reason, I have identified that a grid sampling activity is the thing to be doing. The one question that I have about some of the grid sampling is that it isn't always the most appropriate thing to be doing for the whole farm. And so in this particular example here, the grid sampling has really neatly mapped out the pH and how it varies across the farm. They've then gone through the process of identifying what the lime requirements are, but it actually ends up showing that 80% of the farm doesn't need lime. So having spent $10, $15, $20 a hectare, whatever it costs to do the grid sampling, to identify that you don't actually need to do any lime application, it raises one of those questions of, could you have done something prior to do the grid sampling to actually identify that there are large sample or large parts of the farm where the intensive sampling isn't required. And so I think, again, it's this whole idea of multiple layers of information and making informed decisions rather than having some kind of blanket recipe is more likely to be a much more robust way of going about the process. And it's one of those things that when we do go about the process of targeting investigations and coming up with variable rate plans, or even just the most appropriate rate. And that's something that people often forget, is that you don't have to be using this technology to go down the path of variable rate application. Quite often we're using all this technology simply to identify where are the most representative parts of the paddock to go and do our investigations of the soils or the crops or whatever we're looking at. And from that come up with a whole paddock recommendation that we know suits the bulk of that particular paddock. If we've identified the extent of variability does justify some variable treatment, then actually generating variable rate maps, putting them on equipment these days is really a quite straightforward process. And there's lots and lots of farmers and advisors out there that are doing it and getting spectacular results that are able to make crops much more uniform in some instances, or simply to achieve the potential, which in one part of the paddock might be a low yielding potential relatively to a high yielding potential somewhere else in the paddock. And so essentially it really is about targeting where we're going to do our investigations and using multiple layers of information. And so the take-home message from all of that is that I think it makes a lot more sense to be making incremental steps that ultimately going from whole paddock management to most representative part of the paddock management to then zone management to then grid management would seem to be the most logical process, and that we're not assuming that there's some magical recipe that's going to allow us to do the same set of activities in every paddock, that we need to tailor our entire process to the individual paddock requirements, and that understanding the landscape is really what we're about, and that ultimately comes back to understanding the soil and the potential of the soil that we're managing. And critically, if we're going down this path, that the data quality has to be known. We need to really understand what's the data that we're using, where did it come from, what's been done to it before I want to start using it. And that quite often, a lot of these processes really aren't for the individual farmers to be doing, that it can really work to find some kind of trusted advisor or trusted source of assistance to be able to step you through the process for utilising all this spatial information. And finally, in talking about this, I think it's always quite important to remember that all this technology that's out there, that the fundamentals of agronomy and crop management haven't changed. That was back in the 1830s that a German soil chemist devised or promoted what he's calling the law of the minimum, that crop production is determined by the most limiting factor. And while at the time he was talking mostly about nutrients, we can equally apply that to water holding capacity, compaction, biological activity, that we really do need to find what is the most limiting factor, address that, and then start our process as we head down this path of identifying and assessing patterns in paddocks. So, Abby, that's where I'd like to wrap it up for this morning. And yeah, throw it open to the audience for some questions.
Fantastic. Thanks very much, John. Really interesting presentation, and I'm sure everyone was really interested. Thanks, everyone. Thank you very much again, John. It was great.
Thank you, everyone.